Okay. Hello. Because I think I'm sick, even this Tuesday, maybe I cannot talk too loudly. Okay. I think I have some problem. Okay. In fact, this week we started to know more about the compressors in our refrigeration cycle. We know the function of a compressor. The function of a compressor in the refrigeration cycle is to take a certain amount of refrigerants and compress it to a high pressure, to the required high pressure. And for compressors, we have learned there are several types. Okay, there are several types for our refrigeration system, in fact, including centrifugal type, reciprocating type, and screw type. There are three common types of compressors. So based on the types of compressors, we have reciprocating chiller, and screw chiller. And we have to understand that reciprocating compressor, chiller, and even for our home air conditioner, they are using reciprocating compressor. So it's suitable for small cooling capacity. Centrifugal chiller, centrifugal compressor are suitable for large-scale cooling capacity refrigeration system. So for the compressor, we mainly introduced. Okay, for the compressor, we have three main types. We reciprocating type, and the screw type. For screw type, I think we will not go into the details. And centrifugal type. And the centrifugal type. So, in fact, we mainly introduce the working principle of reciprocating type. And next time, yes, we will introduce the centrifugal compressor. For reciprocating compressor, we understand that is to show there's induce some low pressure vapor into the cylinder, and then compress it to a smaller volume. So therefore, the temperatures will increase. And we have to understand for reciprocating compressor the different strokes and also volumetric efficiency. Okay, we know clearance shall be provided. Okay, for the operation of our cylinders. For reciprocating compressor, so we know that usually there are several numbers of cylinders. Okay, for not only one, so sometimes we have 2, 3, 2, 4, 6 cylinders for one compressor. And now let's work on example number 1 together. Okay, maybe I leave you. In fact, for example number 1, we have learned. We have learned during our lecture. So, however, I would still like to leave you a few minutes, especially on part B, because part B is related to the geometry of the cylinder. Okay, I leave you Okay, so maybe we work on example number 1 first, then we spend some time on part B. For part A, we have to be careful. It's a single-stage reciprocating compressor. Okay, so we should know how to use perfect gas equation and also to calculate after compression the delivered temperature. So we can see the equation and also the indicated work. Okay, and we also need to remember the deriving process for this indicated power. And for B, I think I wish you could spend some time on it first. So before you read the question, as I have introduced during our lecture, so the ball is the diameter of cylinder. Okay, so look, you can consider is the valid length of the cylinder. Okay. So then you need to know how to calculate the volume. Okay. So I give you 2 minutes, maybe 3 minutes to read part B, and then we will work on it together. Don't feel comfortable, so I call a book. I will see the doctor after. Sorry. Okay, so it's related to we have to understand the working principle of the cylinder and also the geometry design of our cylinder. So for this one, I think because the volumetric appearance, so we will think So firstly, we need to read the given conditions. Is when the compressor is driven per minute. Okay, that means okay, it can have so one cycle, revolution cycle. 1 minute there are 300 revolution cycle. So for each cycle, we remember we will there's okay for each we remember there's induced stroke, induction stroke, and then a closed system, and then is compression, and then it's delivery stroke. There are 3 stroke. Okay, this is called one cycle: open, close, compression, and open delivery. Okay, so then we understand this is one revolution. Okay, intake and deliver and discharge the high pressure vapor. Okay, and so any further information we know is a single cylinder machine. Okay, single acting. So we also understand what is single acting. So we know this is only one single cylinder. So we are asked to calculate the cylinder bore required, assuming the bore and stroke to bore ratio is 1.5. So this is for the design of our so this is the cylinder. Then we understand that. Okay, this is the stroke. And the diameter is bore. Diameter of the cylinder is called the bore. So we know the stroke to bore ratio is 1.5. And then we ask to calculate, besides the cylinder bore, the geometry design, and also the power of the motor required to drive the compressor. So because we know here is this is indicated power, but we remember we also need to, if what's the actual power input, in fact, we also have to consider the mechanical efficiency and electrical efficiency. Okay, so this is the actual power, then it's simple. Okay, now let's have a look what's the information we can get. So because this is from the given conditions, we know 1 minute is take 1 cubic meter vapor. Okay, I think here this is air. Okay, air. 1 minute we take 1 cubic meter, and also we know 1 minute there is 300 revolution per cycle. So therefore per cycle So the per cycle, the mass or the corresponding volume we take is 0.00333 cubic meter per cycle. And so then we understand this is the volume. This is the volume of the. This is the volume. Okay, this is the volume, swept volume. We can consider is also swept volume. So because this is per cycle, so we understand the cylinder volume is 0.00333 cubic meter. So therefore, we know the to calculate the cylinder volume, we know the ball, and this is the stroke. Then we can calculate the relationship. We know the ball and the stroke. There is a stroke to ball ratio. So then we can calculate through this equation. Okay, we can calculate the ball. Okay, we can calculate the ball, and then in fact for the work we consider the mechanical work and electrical work. This is the input work. Okay, input work, required input work, because this is the indicated power. Indicated power, so we can use show the reversible work for compression process. Okay, that's deriving process during our lecture. Okay, this part I think we just don't need to consider it. Okay, so this is for the design of cylinder. Okay, I think I will leave you 5 minutes. See if you have any question on example. Because for this one, you have to understand the working principle of reciprocating compressor, the cylinder, and also the geometry of the cylinder operation. Okay, I give you 5 minutes. Then if you don't have any question, you can continuously work on example number 2. So example number 2 is a question regarding multi-stage with compression refrigeration system with a specific compressor type, is reciprocating compressor. Oh, okay. I found that we are not interactive. Okay. No questions from you. Okay, I accept because some of you will approach me. So after tutorial session, also today I think I'm sick. I need to go to see the doctor. Okay, now let's work on example number 2 together. So still, I think I wish you could read the question first, and then okay, this question is regarding the question. Okay, we have to consider with clearance. Okay, with clearance. So for this one, without clearance. Okay, because okay, maybe we work on it together. So this is we have to read the given condition. So the first question, example number 1, is a single cylinder. So this one is with a 4-cylinder. 4-cylinder. 4-cylinder single acting, but it's also a single acting. 4-cylinder single acting compressor with cylinder bore 80 mm and stroke 130 mm runs at 680 revolution per minute. So we have to be familiar with the unit. And the ambient air pressure and temperature are 1 bar and 30 cubic meter per second. So if the volumetric efficiency is 89%, we ask to find the mass of mass delivered per hour. So therefore, we can see is to take the air, okay, to compress it. We know the geometry design, we know the bore and the stroke, and also the revolution per minute. So it's 1 minute. So it can complete 680 cycles. Okay. Then let's see. We ask to for this cylinder, how much? What's the mass of air can be delivered per hour? Okay, here is per hour. Here is per minute. Then we need to calculate the swept volume with the given one, swept volume. Okay, for the swept volume, it's easy to calculate. Okay, then we calculate the swept volume of the cylinder. So therefore, if the take the air at this pressure and the temperature, then we can calculate by using the perfect gas equation. So we can calculate the mass of ambient air that will fill this swept area. However, we have volumetric efficiency. Okay, volumetric efficiency. Then this is the without clearance. This is the mass of ambient air which can be induced by this compressor. Okay, then we consider the compression efficiency. We got so per cycle. This is per cycle. Okay, per cycle, we can induce this much of air into the cylinder. okay, into this is 1 cylinder, okay, this is for 1 cylinder. So therefore, the actual mass flow rate per hour, okay, per hour. So we can see, one, we need to consider 4 cylinder, okay. This is a single acting. This is 1 minute. How many cycle? This is 1 cycle. The per cycle. So this, then the results will be per minute. Okay, induced mass flow rate. Then we want to know, get the is per hour. Okay. So this is for example number 2. Still, I think I will leave you 2 minutes. See if you have any question on example number 2. If you don't have, so you read example number 3. So I leave you total for 4 minutes. Okay, now let's work on example number 3 together. So for example number 3 is different type of two-stage vapor compression refrigeration plant. So with a flash chamber, but there is a direct contact of the refrigerants in different loop. And what's new here is we know the compressor is single-acting, single-stage reciprocating machine, the boost compressors. Okay, single-acting, they are reciprocating compressor with 4 cylinders. Okay, with 4 cylinders, and we know their isentropic efficiency. Okay, and also for the compressor, they design the stroke bore ratio is 1.1, and in fact, through the speed, we can calculate the mass flow rate. So it's 480 revolution per minute, and also we know the volumetric efficiency. So similar, we know there are 3 pressures. The required, the high pressure 10 bar, and for flash chamber is a 3 bar, and for the low, for the evaporator is 1 bar, and for 3 and 5, so we know there's no superheating and supercooling. So, and also know for state 1 is superheated by 10 Kelvin degree. As we learned, in fact, sometimes the expansion valve can be also used to control the superheated degree. And then what we need to know, calculate if we ask the power input, okay, the 2 power input, and also to calculate the stroke and the bore of each cylinder, okay, the design of each cylinder. Firstly, I think the first step is always we need to draw the processes on the pressure enthalpy diagram or temperature entropy diagram. So then we can see that so there is a mixing process between here there's a this is a mixing process, and from 1 to 2 is irreversible process, not isentropic process. Okay, and from 3 to 4, but 1 is superheated. State 1 is superheated. So now let's see. And because we know the isentropic efficiency, so we can calculate the actual. So for the 2s for isentropic one, because we know the pressure and its entropy, so we can calculate. We can get the actual enthalpy of state 2 and state 4. So for the evaporator, then we know the refrigerating effect. We know the state of 1, the value of enthalpy, and state 8. State 8 is equal to, 8 is equal to 7. Okay, then we can get for the evaporator, the mass flow rate is 1.39 kilogram per second. And always with the flash chamber, we can apply the energy equation of first law of thermodynamics for open system. Then we can calculate for the through the condenser and for the high pressure loop, the mass flow rate. Then we can get the power input, okay, of the low pressure compressor and the high pressure compressor. Low pressure compressor. So for each low pressure cylinder, because we ask to calculate the bore and the stroke of the cylinder. So first we need to remember is each one is 4 cylinders. Okay, so for the low pressure cylinder, okay, this is for low pressure cylinder. Okay, then we got the mass flow rate of refrigerants. As we know, for volume 1, because we know for the state 1, this is its specific volume, then we can calculate at the beginning. So, no, is with yes, for the state 1, this is for state 1. Specific volume, state 1 specific volume. Then we can get we can calculate the actual induced volume. Okay, this is the one induced volume. Okay, this is the one induced volume. Okay, however, with the clearance, okay, this is induced volume through the mass flow rate and specific volume. However, due to the volumetric efficiency, we know the actual swept area. Okay, actual swept area. Okay, over the volumetric efficiency, we can calculate the value. This value is the swept. So be careful with the different volume. Okay, this is the clearance. This is the swept volume. But with the clearance, the induced volume, the ratio of reduced volume over swept volume is the volumetric efficiency. Then we based on the calculation. So this is okay. Then the swept volume per second. Okay, and then for each stroke, because we know the per second, so it's 8 cycle. So for each cycle, so then we can calculate the swept volume. Okay, we know the swept volume through the equation. We can calculate the bore and stroke. So it's for high pressure cylinder, it's similar. And but here I have to say, we have to be careful with the values, the volumes. So we can see there the volumes, the total cylinder volume. Okay, there's a total cylinder volume. Okay, here is using VA. Okay, this is a total cylinder volume. And then we are very common to use is swept volume. Okay, so for this one is we can use how to calculate. So we can use swept volume. Okay, this equation is to calculate, because the stroke is the moving distance, okay, the distance of displacement distance of the piston, of this piston, okay. So this one is used to calculate, okay, swept volume, the relationship. However, we also have the volume is called induced volume. So for induced volume, so we can say is the induced volume of vapor into the compressor. Okay, this one we can use to calculate, we can say, related to the mass flow rate. Related to the mass flow rate. And so the relationship is the volumetric efficiency, okay, is the V1 over Vs. So only you understand the relationship of these three volumes, then you can really understand the working principle of reciprocating compressor. In fact, they are cylinders, and you also need to correctly do the calculation. Okay, I will stop recording now because I don't feel comfortable, so my voice may be low. Okay, we still have 2 minutes, so see if you have any question. Thank you for joining me today, because I think every time, so especially Thursday, there are less students to attend our tutorial session. Enjoy your holiday. Okay, so after holiday we need to prepare for our exam, so don't worry, because it's take-home exam. I know it's easier, it's difficult to fail you. However, so if you aim high, then you also need to spend more time, okay, because I need to differentiate. So therefore, the questions may be tough compared with the previous one. Okay, thank you.